I am Ben Beddisworth. I'm an engineer at Tentley. I do senior engagement analytics. Sorry, I am a senior engagement analytics engineer. I have a graduate degree from UAF in computer science, and I kind of know, I think, a little bit about machine learning and AI. So we're here to talk about some of that. So what is this talk? This talk is about TensorFlow and more of the technicalities of how to actually use it. So actually like making a neural net, putting data into it, making predictions, and actually training it. So it's intended at that sort of target. If you've never seen TensorFlow before, this is very good for you. What this talk is not a mathematical lecture. It's not comprehensive, and it's not even the best way, I think, to solve this problem. It's largely just a more interesting problem than you'll find on a lot of tutorials online, which I was really actually, the real driver for this talk was that a lot of the tutorials online are actually kind of bad. They use the same data sets, it's not very interesting, and really there's no reason to use such a complicated structure to do it with, to do the training. So we're going to talk about what is AI. Some people might not know what that is. AI is a general class of problems where it's problems for computers where humans are actually quite good at it, but computers tend to be quite bad at it. So that's things like natural language. That's things like computer vision, like seeing things. Seeing that's a dog in a picture is really easy for humans, really hard for computers. Games, chess, checkers, Go. Dota was recently broken by OpenAI. There was a big thing from OpenAI where they beat one of the best players in the world using a bot in Dota. So the problem I've arbitrarily chosen, because it's relatively easy and actually complicated, but interesting, is determining gender. So the idea is we're going to take a photo, any photo at all, of a person, and figure out what's their gender. So to do that, we're going to have to extract their face, and then estimate their gender, because there will be some error, as with most machine learning. So as it's usually the case, when you start on a problem, it's good to look at the tools you have available to you to actually solve the problem. The tools we have in machine learning are actually quite a lot. We have HAR-like features, which is we'll be talking about. We'll have concurrent neural nets, but also things like facial analysis that looks at landmarks. We have what else do I have up there? Decision trees, where we could actually look at the facial landmarks and make some decision about their gender based on those trees. And then there's tons of libraries which support this, right? There's OpenCV, which we'll be using. There's TensorFlow. There's a bunch of APIs, Google Vision, Face API, Amazon Recognition, and others. There's the scikit-learns and things like that. But we're going to be focusing on two. We're going to be focusing on OpenCV and TensorFlow. Because this talk is about TensorFlow, and OpenCV actually happens to be quite easy to use. The other ones are fairly complicated, I think. So now that we have the tools associated with us, we can break down the problem. The problem basically comes in two stages. It's to detect the face and then run that face through a concurrent neural network. As you can see, the boxes there is actually where we've detected a face on that in the very good Tentley blue that we've chosen. So once we've found the face, we need to extract that face and actually run it through the concurrent neural network. Or sorry, convolutional. That is wrong. So face detection was a hard problem for a long time until a pair of people named Viola Jones cracked it in, I think, 2002. What we used to do is we used to look for things like eyes, faces, or eyes, nose, eyebrows, ears, because those would signify to us a face. But it ends up being that the structure like an eye is actually quite complicated. It's not very good to see like a face in a picture from far away. Lots of people's eyes, sort of the white of it goes away eventually. So it's hard to actually use that to actually detect faces. Furthermore, they're complicated structures, so it's actually really difficult to compute whether or not there's a face. Oh, did I go? What happened?
It was switching.
Oh, okay. I'm sorry. It's very difficult and complicated to detect a face using these structures. So what Viola Jones realized is you can use something called HAR-like features, which just looks for bands of light and dark. And you can determine that there's a face there really accurately, actually, by using this really simple calculation. It can be done in real time. It can be done in real time by your phone. That's how Snapchat does it. That's how basically everybody does it nowadays. So we're going to take a look at some HAR-like features. So these are some HAR-like features. I'm going to point to D because it's the easiest to talk about. So D is the feature which is supposed to pick out your eyes. So if you look at my forehead, there's a light band, there's a dark band which is caused by the shadow of my brow ridge onto my eyes, and then there's the light band where the light hits my cheekbones. By looking at that, we can find something that we think is an eye. But we're not really sure. We have to actually look at all of these features. So all these features correspond to something. C corresponds, for example, to a nose. And once you have good detection on all 4 of these, or all 5 of these, you have a pretty good chance of actually there being a face there. This is, again, really fast. There's techniques to make this like really, really fast in real time. So now we've detected a face, and it's pretty easy to extract it once you've detected it. We can estimate gender. The way to do that is to actually, we could use facial landmark analysis, which involves looking at facial landmarks. So that's like where the cheekbones are, how far they are relative to the bottom of the jaw, where the jawline actually is, what the brow, the nose is, things like that. That ends up being really, I have to think about that really hard, and I don't really want to do that. That's sort of the point of TensorFlow is you don't have to really know a lot about your problem to be able to solve it. So we're going to use a concurrent neural net in TensorFlow instead, but that requires quite a lot of data. So you have to tag it first and you know, whatever. So we're going to build in TensorFlow, let TensorFlow do the training, and then we're going to count some accuracy of that flow, of that neural net. So a quick summary of how a concurrent convolutional neural net works. It's inspired by how our eyes actually work, how our vision works, but it's very loosely inspired by that. So what we're going to do is we're going to take some filters, which are just numbers. We're going to take those filters and we're going to look at various subsections of this image that we're looking at and calculate how much it fits that filter. And we do that for every bit of the image. So every place where we could put this filter, we're going to put it there and see if there's something there. The filters usually grab out things. If you've done Google's DeepMind has like a vision thing that you can upload a video, and it'll show like the features that it detects. It usually detects things like eyes, but also things like lines. So it sweeps the jaws, noses, things like that. It's a very general way to actually look at these features and get pretty good accuracy. We're going to take the output of those filters, and we're actually going to run it through a regular feed-forward neural net, which happens to be quite general. It's a fact that a feed-forward neural network with at least one hidden layer can accurately estimate any function on the unit cube in Rn to a closed bound on, yeah, okay. It can do anything you ever want. Sorry, that was a really mathematical. It can solve any problem you ever want is essentially what it's saying, given some pretty mild bounds, like that it's continuous, or continuous enough that you don't care. So once we have a neural network, we have to actually teach it how to look at the world. We have to teach it how we're going to do that. And the technical term for that is training. We're going to run the neural net on a known data set. So that's going to be, we have a known data set, shockingly. And we're going to watch for errors when we do that. Yeah. So we're going to watch for errors. Hold on. And we're going to minimize, yeah, so we're going to minimize the errors of those. We're going to run it through the data set. We're going to look for errors where it misclassifies the gender of the person in the video, of the image. And we're going to calculate why it was wrong by calculating the derivative of this neural net. And basically tell it, we think you were too confident in it being, say, a male, but it was actually a female, so here's why we think you were wrong. Can you please fix that for future iterations? And it does that through calculating a derivative. And that's really the magic of TensorFlow, is that it does the derivative for you. That's really the hard part of neural nets. So we have a data set. It's from Wikipedia. Shockingly, everything's from Wikipedia nowadays. So we have a tag data set. It's got the face locations, which we won't use, but they're nice if you want to do this on your own and you don't want to detect faces. It's really easy, though. It has the age of the person. It has the gender. It has a bunch of other things, but we're only going to be using the gender tag and the images themselves. So now that we have all the pieces here, we have to do the software pipeline. The pipeline is going to be we're going to run the images through a face extractor. We're going to extract those images, and we're going to run them through a neural net, and then output the, resize the images to a consistent size because the neural net is actually really fragile, and run the resized images through the convolutional, the CNN. So we're going to use OpenCV for extracting the faces. OpenCV is a project that was started in 1999 by Intel to do all things computer vision. It's a pretty big library. It's really useful and has lots of tools available to it. In 2012, it became open source, and it's written in C++ and C, which means it's fast, but it has bindings in a lot of languages. I think Java, Python, anything you'd really want to use. It probably has a binding that you can find. To detect faces with OpenCV, we're going to run basically this code. This is a little bit cleaned up to make it look better. What you're going to do is you're going to take the image, you're going to take the cascade, and you're going to grab it out of this file, which is just this XML file that tells you what these features, the features that I showed you on the previous slide, look like in data. We're going to read in the image. We're going to convert that image, which is a color valid image, to gray. And then we're going to ask this magic function to detect multi-scale for all the faces. There might be more than one, so it returns an array of faces. We go through it, and we extract them using NumPy magic, which is the slices in Python. Which is really, I mean, this line is 10 lines, and this is a problem that was unsolvable like 20 years ago. It's pretty amazing, actually, I think. So now that we've extracted faces, we got to build a concurrent CNN. Google's open source, so TensorFlow, what is TensorFlow? TensorFlow is Google's open source solution for neural nets. They developed it internally because they had a bunch of need to do a bunch of neural net data mining AI stuff. And that became so popular and successful that they decided to keep using it all over their product place. So that was including, so their Google search would do stuff, but then they wanted to make sure they could do content tagging quickly, so they moved it to that, for example, etc. It was released as an actual product in 2015, and it's a big freaking deal. If you go onto GitHub, which is the repository for almost all code in the universe nowadays, if you look to start recently starred projects, a lot of them are using TensorFlow. Like a lot of really interesting projects are using TensorFlow. And it's pretty industry standard now. It's a really good way to build a model. It's a really good way to make sure you don't make mistakes. And it's just a really awesome way to do really cool problems. So how does TensorFlow work? TensorFlow works by running in a specialized environment, which they call a session. So it abstracts all the actual running to something that's been optimized and actually fast to do what it's doing. Then you define the various things you need to do with it through this API, this interface that they make. So it's going to let you define data that you are going to vary for your model. It's going to let you define the placeholders, which is the data you're going to hand to it that tells you maybe you're right or you're wrong, or this is the data I want you to classify. It's going to let you specify the functions, what to do with that data. And did I put anything else? Yeah. And you're going to also have to define how to train the neural network and how to tell it that is wrong, essentially. So the data structures in more detail are variables, which are things that TensorFlow is allowed to change to make your model better. Your view of how the world looks. It's going to have, so those are things that TensorFlow is allowed to change. There's the placeholders, which are things you're going to feed into the data to TensorFlow. These are things like images you're going to want to classify, but also the labels that you want it to get right or wrong. This is how we train it. We say, here's the image, here's the label I expect. If those are wrong, we're going to backpropagate that error that said that it was wrong. And the functions that we use to transform that data in our model. So we're going to actually define the model in TensorFlow. Again, I want to emphasize how important that is. The reason why this entire structure is this way, it's actually quite complicated and difficult to use. The reason why it exists is so that functions are defined in TensorFlow. And so that functions have their derivative built into them. That enables you to actually do quick, easy machine learning and propagation of error. It's really quite difficult, actually, like to compute it by hand without doing this. It's really quite, it's really good that Google did this. It really helps humanity by doing this. So this is the semi-arbitrary structure I chose to solve this problem for TensorFlow. we're going to have a 128 by 128 pixel image that will actually be our input. We're going to have two convolutional layers, two fully connected layers, and the output class is 2 because that's how the data came tagged. There's just 2. So there's male and female, or man and woman. So setting up the convolutional layers, this is kind of a big bucket of code. I'm going to try and walk you through it. So this function takes inputs, input channels, and filter size and num filters. Inputs is usually another data structure, and the rest are numbers. So we're going to start by defining our weight shape, which is the filter size by a filter size. So think of that a big block of numbers, which is the size of the filter we're going to look. So that's the little like patch that we're going to be moving around the image and trying to get things out of. We're going to have a number of input channels, which in this case is at the beginning is 3 because it's a color image and there's 3 colors, or most things are generated in 3 colors. And then we're going to have a number of filters we want to actually output to. So you should read that as the first 2 are size, the second one is the size of the input, and the third one is the size of the output. We're going to initialize those things with a truncated normal distribution using the weight shape with a standard deviation of, it doesn't matter, just choose one. And we're going to make a convolutional layer out of that. So that's the inputs. We're going to feed the inputs to that convolutional layer with the weights. And we're going to use strides 1, 1, 1, 1, 1, which means compute the filter for that little window, move it over 1 pixel, compute it again, move it over 1 pixel, move it again. Do that up and down. So basically everywhere you could basically put this filter, we're going to compute the value for that. And then finally, we're going to run that through a max pool. We're going to add a bias, sorry, which is just a constant. Then we're going to run that through a max pool, which just shrinks the image. So it takes the max out of these 2x2 windows and says that's the new value for that. So it shrinks it by half. This is to reduce the amount of noise that's in the, there's a paper recently that came out that talked about this, about the compression of neural nets. This is doing that. It's compressing the information and trying to drop a lot of noise out of the information we're getting so that we don't have a problem with misclassification. We're trying to make the data nice and clean. So once we have all the convolutional filters actually processed, we have 2 fully connected layers that we have to add. They are described here. They're basically matrices, matrix multiplications, if you remember that from high school or maybe college. So we just have a matrix with row size input and a column size output size. We're going to do the same thing where we initialize that to a random normal. We're going to add a bias. We're going to matrix multiply those 2 things together, the inputs and the weights. And then this ReLU is a way of adding nonlinearity to the problem. So that's going to do the magic of the neural net for a feed forward. It's going to make it so that you can't. It's going to do the magic. I don't know how to explain it. It's kind of technical and hard. It's the magic that's to the universal approximation theorem that I said earlier that says that you can actually approximate you can approximate any function on a unit cube and blah, blah, blah. You can do whatever you want. I'm sorry. So finally, we're almost done. We've got 2 more slides of code. I'm sorry. We got to set up the cost and the optimizer. So the cost is essentially how wrong we are. So how much I should move my predictions, or how much I should move my weights because I'm wrong by a lot, for example. We're going to optimize that using something called softmax cross entropy with logits. That's a lot of technobabble to say how well does my model fit the data. And it happens to be there's lots of ways to do that, and we've chosen this one. We're going to take the mean of that crossmax, which is a number, it's a number greater than 1 or greater than 0. And we're going to do this atom optimizer, which is like a gradient descent, if you know what that is, but it's a little bit smarter. It happens to know a little bit of history, so it can make better decisions about what it should do in the future. So finally, we can train the net. So TensorFlow has this really nice feature called the data set, which makes it handle your data for you. So I have this data set called train. I'm going to tell it to shuffle the data in this buffer of 1,000, because I don't have that many. I'm going to tell it to batch it in sizes of whatever I want. I think it's 32 in my net train batch size. I'm going to make an iterator out of it. and then I need to make a function of that iterator because that's how TensorFlow works. It just needs a function to be able to get the values out. And so what we're going to do for as long as we can is take out the X batch that we want and the Y batch that we want, which is our inputs and our labels. We're going to get them out of session.run getNext, which is the function for the iterator where we get the values out. We're going to feed those into the optimizer via the feed dict, so that will actually do the computation, the gradient descent that we've described earlier, and then it'll throw an error out of range when it's done, and we'll just break when we're done. So that'll define an epoch, what that's called. It means that we've gone through the data once. We got a demo, and kind Erik here will help us with this. Okay, cool. So this is the actual code that's running. What I presented to you in the last slides were a little bit cleaned up for the purposes of actually just getting the essence to you. There's a lot of not interesting code here that does things. So like in the get faces, you can see down there, I have a bunch of things to just get the path correct, which is really an uninteresting problem in computer science. Thank you. And so I took it out for the case of that. And there's the case that image read will fail, so I had to get rid of that. It's just I took it out. And then I have this data structure datum, which I use to actually move the data around to all these other functions. Yeah, so can we move down to make gender vector? Yeah, there we go. So at the top there, you can see make gender vector. So I say that if it's a male, it is the data that I have. If it's that, then I make it a vector of 2. So this is called a one-hot vector. It's just a technique that we use in machine learning. And then skip past make data sets. That's also interesting code. Egg to TF placeholder, where we actually define. You went too far. There we go. So TF placeholder is I'm defining. This is where I'm going to put my input data when I make it. Y true is also a placeholder. That's the true labels that I'm going to place the things. So this is the placeholder variables we were talking about earlier. Then we're going to, there's the 2 functions we talked about for make convolution layers and make connected layers. We're going to make them down at line 26 right now, which is not actually line 26. It's relative line 26. So we're going to make them. We're going to make them with the first input being the actual input, with the number of channels, which is 3 because it's a color image. The number of filters we want, which is defined up there, it's defined to be 20. And the next one's defined to be, it's 20 for the convolutional size and 32 for the num filters. And then we do the same thing for the second one. We flatten it because of uninteresting reasons to make the data sizes match up. Then we make a flattened layer. We make another flattened layer. We use softmax to do the final bit to make the repeated. That normalizes the thing and allows us to do one-hots. We have our optimize function again, which has a little bit more just print out stuff, uninteresting stuff. Down to the bottom, that's cap G. We'll do that. No, down to the bottom, cap G. Or GG? Yeah, so, no, cap G. There we go, okay. So then I'm just gonna run this for a while. So that means I'm going to do 2 epochs, then I'm gonna print out the accuracy. Generally you batch your stuff into test and train. And then we're gonna save it. So I've been running this for a while now. I started last night and it died, and then I started it again this morning. It was really frustrating. Mac decided it needed to run updates more than it needed my data for my talk today. So, so the demo isn't quite as done as I'd like it to be. I'm really sorry, but we can move to the next window, wherever it is, question mark? Yeah, so here it is. So what we have is, if you scroll up to the top of when this started, oh, so many years ago, it started out with really bad accuracy, with 21%, 28%. That's on actually training the data. After we did a full epoch, we got to 72%, which is significantly better than guessing. We should expect 50% on gender. But if we scroll down as it goes on, we've actually gotten to, I think it's pretty close to, oh, is it going down now? We got up to 80%, 90% almost, and now it's going back down. That's a feature you can overtrain on accident. Yeah, so let's go to, yeah. So that's I want to show that because if you looked at that, that was about 200 lines of code to do something that was quite impossible or quite difficult to do. You basically did it only in research institutions, like as recently as 5 years ago. TensorFlow has really changed the game in terms of how we can make neural nets, how we can do AI, how we can apply AI, and it's a really big deal. I hope you guys have all seen this and been inspired to actually go out and like write your own AI because it's actually really easy. There's tons of great tutorials online. There's tons and tons of great tutorials online. I happen to choose this one because I liked it. Here's some resources. Yeah. That last one is really good. I've used it before. Yeah. Any questions? Oh, thank you. Yeah.
So one criticism of AI is that it's hard to see how it works. So what methods do you use, or do you let your customers know that lets them understand at least how it works? And
Right. Okay. Yeah. That's a totally legitimate question. So the question was, what do we do to give confidence in our AI models, basically, if I'm rephrasing it, when we don't actually know what's going on? And the answer is the same way we do a lot of science, I think, where you just try and fiddle with a lot of things. You try a lot of things and see what works best. In particular, if you noticed, I actually reserve some of my data for testing, and I run it against that. So the idea is that I'm actually running it against real-world data. And that should, if my model is good, give really high accuracy. That's the best thing. There's been recent papers and recent work on understanding how neural nets work, to sidestep the question a little bit, which I referenced a little bit earlier. There's this idea of information bottleneck, which says that it's throwing away information. And we have some insight now, very recently, into how they're actually working. But it's still not clear like what features it's actually picking out. I mean, do you believe in gravity? Because it's about the same level of like, that's the same method you're going to use. You're going to use some empiricism to get to get some confidence in your model, essentially. Any other questions? Yeah?
So, is anybody using this in the form of like calligraphy?
Calligraphy.
Looking at your audio or looking at a presenter
Uh-huh.
and looking for tells that point to honesty or dishonesty?
Yeah, Tentley is doing something like that. It happens to be that Tentley is I'm not going to pitch too much. Tentley is doing something like that where we're doing crowd engagement. So we are doing that. We aren't doing it for lies, particularly for presenters. We're doing it for the crowd. I'm sure it's really hard to find a data set where you know somebody is lying versus not lying. It's harder to define what that data should be. So you take an image. It's a still image. Are they lying in that image? Are they not lying? You can do something with something called recurrent neural nets. So they have some memory. And you can play video over those and get some idea what's going on. So they're lying in this video, and that gives you a better idea. I don't know of anything specifically, but it's certainly reasonable. And you could absolutely do it in this.
This seemed really like an interesting outtake of what you're doing.
Yeah, it is. Yeah.
How large of a data set are you using for training in general?
In this one, I am using like 15,000 images. The full data set that I got from this data set that I downloaded off of Wikipedia is like 75,000 images. I did that largely so that I could train the model in time. More data is usually better. Yeah. You need lots. They're actually training their model through you to actually, like, yeah, that's how that was the first captures, was to do optical character recognition. So they would randomly give you a known prompt and a non-known prompt. It was semi-random. So one of the answers didn't matter, one of the answers did matter, or sometimes they both matter. Point is that Google is using you to farm all their tagging data off. And there's actually services out there where you can be more honest about it. I forgot what they're called, but they're like mechanical tricks. Thank you. Yeah, where you. where you get paid like 3 cents for every 1,000 you tag, or you pay that much for every 1,000 gets tagged.
So you use 15,000. What do you say is your boundary, like your lower boundary of how big of a data set you need to accurately train?
It really depends on how complicated the data you're attempting to model is. The MNIST, the standard thing that everyone uses for TensorFlow things, it's handwritten digits. I think that's like 100,000 images. And I mean, more is better, but I wouldn't send this until you have 1,000 data sets, data points. You really don't get anything big enough. You don't get enough like actual real world noise to be able to drop that to actually believe your net's going to work in the real world until you have about 1,000. As a random number, I mean, you should believe that as much as you believe the 30 for statistics. It's a hard problem to ask that question. Yeah. Is that? I can answer all questions all day. Hey.
Cool. I have a question.
Yeah.
So you sort of jumped straight into the CNN
Yeah.
being the solution to the problem, but
Right.
of course you did say that there was the
Yeah.
opportunity to go do this through like behavior analysis, or you could do this
Yeah.
through some sort of human analysis, and I'm putting in some human biometric
Yeah.
data pieces that you think there. And it seems interesting. It's like everyone's using like the AI CNN type solutions as being the way of solving your problems.
Mhm.
It's very TensorFlow at it.
Yeah.
But it still seems valuable. You can get away with a much smaller data set.
Yeah.
You can throw in some additional human knowledge up front.
Oh, absolutely. So absolutely. The question is, did we give up when we, if I can paraphrase, did we give up when we start using neural nets? And the answer is, I believe, yes. We sort of said that we can't understand the problem well enough to actually understand it. So we have this thing that just describes anything that we'd ever want it to. And again, the problem is, you asked this question, it doesn't give us much insight into the problem by doing this. That's an open area of research in AI. I guess I'll have to not answer your question. I'm sorry. Seeing no other questions, thanks for coming. I'm sorry if this was as boring or not as the level as you wanted.
Don't apologize.
Yeah, no, end on a high note.
Or alternatively, you were all blessed by me for having come here and learned this from me.